Okay, so today inshallah we will continue discussing how to design this simple structure of lead lag bar system stabilizer. And yes, this is the bar system stabilizer. We will focus on delta omega as an input signal. It could be delta B, it could be delta F, any change in frequency, and so on. So, okay. As we discussed earlier in the previous handout, the idea behind the bar system stabilizer is to provide us with phase lead through these blocks to compensate the phase lag or created by this automatic voltage regulator block, and also K3 over 1 plus STDO prime K3. So how to design means how to find the gain and the time constants T1 and T2. The TW, as we will see in a few minutes, the TW will set arbitrarily high, like 5 seconds or 3 seconds. Sometimes you have it 10 seconds, and this is constant, and we will see why we have such a high time constant compared to T1 and T2. We need this block to provide us with phase lead, so definitely T1 will be greater than T2 in order to get the positive phase angle for this block. Angle of numerator minus the angle of denominator, and phi here equal to tan inverse the imaginary part of this, so it's j omega, omega T1 over 1 real part minus tan inverse minus the angle of the denominator, which is omega T2. So we need T1 to be greater than T2 to have here a phase positive angle, so it will compensate for the lagging angle through these blocks. So you have here the bar system stabilizer signal, and this signal passed through these blocks, so we experienced phase lag, so we need to have the bar system stabilizer here to provide phase lead in order to compensate this phase lag. So this is the idea, and we will see how to proceed in steps. The procedure here in steps, very simple steps, and we will see now. As we mentioned, how much omega n? How do you get omega n? Omega n equal to square root of base speed, which is 377, multiplied by the linearization constant K1 over the machine inertia M. So you can get omega n. So we need to have the phase lead at this frequency of oscillation. So we calculated omega n at the beginning. Omega n, as we mentioned, equal to this. Okay, if you have the linearization constant, then you can get the natural frequency of oscillation. Now we can find out how much phase lag that we have in this block diagram. How much phase lag? This is the control signal, and this signal will go through this block or this block diagram. So we need to find the angle of this transfer function between this signal and the output here. طبعا ال K is constant, the angle of K is 0. يعني this is the angle is 0, so this block will not affect the angle that comes here. So can we reduce this block diagram you have the signal here as input. The signal will go this way right away to here, and we have here a negative feedback through K6. So can you get the transfer function of this part of the block diagram? This will be multiplied by this. This gives you G, and this is H. This is H, and this together is G. So G over 1 plus GH gives you the block diagram or the transfer function of this part. So you can, this is the GE, a transfer function between UPSS and the EQ prime can be calculated as such. This is exactly G over 1 plus GH. Yes, Omar, you have a question?
Yes, in this case, what happened to K4?
What are?
What in the block diagram, in the
What are what?
what happened to K4?
What happened?
K4 in the diagram.
We are not interested in K4. We are getting, this is our input now. Now we need the transfer function between this input and the signal here. So if you are handling now one input, and this is of course you can deactivate the other inputs.
Okay, we are still doing superposition.
Yes, so this superposition for linearized system.
Okay.
You need the transfer function between this signal only and the output here. Okay.
Okay,
So the K4 doesn't play any role. The K5 doesn't play any role.
Okay, thank you.
So this is the transfer function. Okay, the two blocks over 1 plus GH. H is K6 here. And you can, of course, get the angle of this, of this complex number if you substitute S equal to J omega N. And the omega N is already calculated. So you can have here a complex number and you can get the angle, and definitely the angle will be negative. Okay, the angle of numerator is 0. So you can get the angle of denominator, it will be minus. So the phase lag can be calculated from this at S equal to J omega N, and we expect this phase is to be negative. This angle will be negative. Okay, now we calculate the phase lag. So we can get now the angle requested from the bar system stabilizer. If this angle is minus 30 degrees, then this is the angle of GE. Then we need the angle of the bar system stabilizer to be plus 30. So the summation of bar system stabilizer and this transfer function becomes 0. So if you calculate this angle, then you know how much the angle needed from the bar system stabilizer. And if this is the block of the bar system stabilizer, 1 plus ST1 over T2, then we can say the angle phi of this block, which is equal to plus 30 here, known now, equal to tan inverse omega n, which is known T1, minus tan inverse omega n T2. So we have here one equation and two unknowns. We need T1 and T2. You can select, usually this is always the case in the design, you can select one of the time constant and you can get the other. Here you can select T2 equal to 0.1 second, for example. If T2 equal to 0.1 second, we can get this angle, and then we can get T1 accordingly. So this is the way to design 1 plus ST1 over 1 plus ST2. So the summation of the angle should be 0, and this angle is negative. We assume the block the lead lag block of the power system stabilizer is as such. This B could be 1, could be 2. If we may need 2 blocks for higher angle, and so on. Or you can have different time constant, 1 plus ST3 over 1 plus ST4. Anyway, let us assume it will be equal to 1 at the time being. Yani B1 or 2, T1 must be greater than T2 in order to get phase lead. There is a phase angle limit that compensation block can provide, and T2 cannot be too small. You need the T2 equal to 0.1 second, 0.2 second. For example, T2 equal to 0.2 second. If you select T2 equal to 0.2 second and the T1 equal to 10 second, 10 T2 يعني 10 times 0.2 يعني 2 second, and this is 2 and this is 0.2, this block will give you an angle equal to 34 degree if the oscillation frequency equal to 1 hertz. Okay, so omega n here equal to 2 pi, which is 6 point whatever. So what we want to say here is the block, each block is limited with an angle. If you need more angle, you can easily add another block here. This could be 2, or you have different time constant here. So assume that we have, for simplicity, we assume in T equal to 1. B equal to 1. As we mentioned, as we defined there, we have this angle, so we can get this angle and this angle equal to phi, which is tan inverse omega n T1 minus tan inverse omega n T2. So here we can set T2, assume T2 equal to 0.1 second or 0.2 second. Then you can have this angle, tan inverse, if this is muscle, for example, 10 tan inverse 1, which is 45 degrees. So you can add this here, and you can get the angle, or can take tan of both sides. So you can have omega n T1 equal to tan of phi plus that angle. So you can get the T1. You can solve for T1. Is it clear? Okay. Now KC, we design T1 and T2. Actually, we assume T2 and then we get a T1. This is our design for the lead lag block. For KC, we need to amplify the signal. We need to multiply the signal comes from the power system stabilizer by the gain here. And if you go back to the material improving power system damping, we can have this zeta n equal to this. When we linearize the swing equation in the last handout, we have zeta n equal to this, and omega n equal to square root of omega b k1 over m, and this is zeta n. So assume that there is no damping that comes from the mechanical part. There is no damping in the system due to friction and windage and so on. And we have only the damping comes from the power system stabilizer. So this is dE. In this case, dE equal to zeta n to m omega n. Omega n is known, m is known, and you can set here, again, set zeta n. You can say, now I need this power system stabilizer to give us a damping coefficient equal, for example, to 0.5. You assume it as such. These are the design specification. I need the damping or the damping coefficient of the system to be 0.5. So you can assume zeta n, and then you can get dE, and the dE, which is if you look at the gain throughout, if you look at the gain throughout the UBSS, And if you look here at the complete gain of this loop, yes, here, where is the gain? This is KC. We have a gain here, KC or GC or G bar system stabilizer. You have a gain here, and you have a gain through this GE, which calculated already, GE. So this magnitude of this GBSS times the magnitude of GE times K2, this times, of course, we have here KC embedded in the bar system stabilizer transfer function. So you can have this DE equal to this. So DE equal to the gain of K2, which is the block there, the linearization constant, KC for the bar system stabilizer, and GC and GE. This is the magnitude of that transfer function that is calculated here. Of course, you already calculate the angle, and also you can calculate the magnitude of this. So you can get the magnitude of GE, and also you design T1 and T2. So you have the magnitude of 1 plus ST1 over 1 plus ST2, and then you have LKC, and then you have LK2. So this is equal to DE, which is 2 zeta n omega n m. All these are constants, are known. M is given, omega n is calculated, zeta n is a design specification, you set it as 0.5. Then a DE is known, and you can have it here. Therefore, you can get LKC equal to 2 zeta n omega n m over this. So this is a complex number. You can get the, you have here 1 plus ST1 and 1 plus ST2. This is equal to J omega n. Of course, you can get the magnitude of this complex number as we have the angle already calculated before. So you can calculate the gain of the bar system stabilizer. That gives you zeta n equal to 0.5 or 0.3 or 0.4. Frankly speaking, in real life, if we look at real life case, the utility, for example, SKICO or SEC or any utility in worldwide, if you have the zeta n equal to 0.1, you are in a good shape. So don't underestimate for low frequency oscillation of having zeta n equal to 0.3 or 0.2 or 0.4. If you have 0.1 in your real life system, you are in a good shape. Okay, so this is the case. طيب, now we have a KC already designed. We have 1 plus ST1 and 1 plus ST2 already designed also. So the remaining is the reset block, STW over 1 plus STW. How to design this block? This is called the reset. Why we call the reset, we will explain it in a few minutes. This time constant is called the washout time constant. Washout time constant. Okay. How to design of this block means how to set TW. How to set TW. 3 seconds, 5 seconds, how much the TW should be. And what is the philosophy behind this block? Why do we need this block? What is the function of this block? The function of this block is clear now. We need this block to provide us phase lead, a certain angle, and also we need from the KC to increase the system damping coefficient. So KC, we know the idea behind it. T1 and T2 also, we know the idea behind the design here. So what is the idea behind design TW or this block? What is the function of this block? Let us see the function of this block. It should be activated only. We need from the power system stabilizer to be activated only if we have oscillation. If there is no oscillation, we need the power system stabilizer to be deactivated. We don't need anything from the power system stabilizer if the system is running at steady state. So we need to deactivate it. This block actually is doing this mission. This block is a reset block for the power system stabilizer at steady state. Look at this block and see at steady state means what? Steady state means what? Steady state means S equal what?
Zero.
Equal 0. If S equal to 0, if S here equal to 0 at the steady state, what is the gain of this block, or what is the function of this block transfer function? What is it?
Zero.
0. At steady state, this block becomes 0. 0 means we deactivate the power system stabilizer. There is no signal comes out here, and we have here 0. This is at steady state. Type at the oscillating frequency. At the oscillating frequency, disturbance. We need this block to be like with a gain equal to 1. Let us say, for example, the oscillation frequency or high frequency oscillation, if S equal to infinity. Let us go to the extreme case. طبعا عندنا S equal to J omega N, and omega N between, as we mentioned, if you have frequency between 0.1 hertz or 0.2 to 3 hertz, that means omega is belonging to up to مثلا for example 1 radian per second to 18 radian per second. So this is the range. So assume that S equal to 18 مثلا. Okay, S equal to J18. J18, high frequency. You have here high frequency, J18. If this is J18, so this becomes J18 TW over 1 plus J18 TW. Okay, now we need this block not to interfere if we have any oscillation. So if you have such oscillation, you can approximate this one as 0. You can neglect this one. This one compared to this part is very small. So you can say no, this one is not there. You can delete it. You can remove it. So in this case, you have the gain of this block becomes the gain of this block becomes what? Becomes 1 with angle 0 at the high frequency. So that means when this block doesn't affect the operation of the power system stabilizer. It doesn't affect the angle. It doesn't affect the gain. It is just a block with a transfer function equal to 1. It doesn't interfere with the angle and doesn't interfere with the gain. So this is the idea behind this reset block. We need this block to deactivate the power system stabilizer at steady state. If we have any oscillation, this block, the gain of this block becomes 1, and it doesn't interfere with the operation of the power system stabilizer in terms of the gain and the time constants. So this is the idea. In order to have this approximation, ان ال1 ديت تبقى يعني almost 0, we can neglect it. We need the TW to be very high. TW to be 3 seconds. So this is becomes J54, J54 1 compared to 54. Of course, we can neglect it, or 5 seconds or 10 seconds. So this is the way you can set it TW here. The function here, it should be activated only when low frequency oscillation begins to develop. It should be automatically terminated when the system oscillation ceases. It shouldn't interfere with the regular function of the excitation during the steady state operation at the system frequency. This is the requirements of that block. It shouldn't have any effect on phase shift or gain at the oscillating frequency. Having these issues, then you can say TW, we can set it as high as 3 seconds or 5 seconds or so. So in this case, you can just set TW between 3 and 10 seconds. So this is the way, and you have here a transfer function at the oscillating frequencies approximately 1 with angle 0. So of course you can after designing the power system stabilizer, designing the power system stabilizer means we need to set the TW, we need to find the KC, we need to find the T1, we need to find the T2. And as you can see, just to summarize what we have discussed so far, TW just set it equal to 3 seconds or whatever value here, higher value. T2 also you select it equal to 0.1 or 0.2 second also, and you can calculate T1 from the angle of GE, and you can calculate KC based on your specification of zeta equal to 0.2 or 0.3 or 0.5 damping coefficient. So you have some design specification, T2 equal to this, zeta n equal to this, TW equal to this. And the two parameters that we need to find out is T1 and the KC. After having this KC, T1, T2, you can go to AC matrix. If you still remember, the AC matrix depends on, here you have some, the entries here depends on KC with T1 with T2. So having been designed, you can go to the AC matrix and dump these values here in the AC matrix, and you can test the eigenvalues, and you can see whether you achieve zeta n or not. And you specify here zeta n equal to 0.5. So when you calculate the eigenvalues here, you can calculate minus sigma over square root of sigma square plus omega square of the eigenvalue, and you can calculate zeta, and you can see how close this zeta after designing the power system stabilizer with the design specification you set here as 0.5. So this is just to validate your design. You check whether it is satisfy your requirements or not. The oscillation frequency equal to this. The damping coefficient is found from this. You can find the eigenvalues, and you can get zeta equal to minus sigma over square root of sigma square plus omega square. طبعا sigma, this is the form, and you can compare this zeta with the design specification, and you can see how close you are. So in conclusion, for the power system stabilizer, you choose zeta n, you set it, T2, TW, and proceed to find T1 and the KC. That's all. This is the design of the power system stabilizer. Of course, you can, once you design this is the open loop. You can check the eigenvalues with the open loop, and you can have now the closed loop matrix. We already developed it. You can substitute KT1, T2, TW, and all this. You can have the eigenvalues of the AC and you can compare between the A and the AC eigenvalues, and the effectiveness of PSS can be also assessed through the time domain simulation by exposing the system to a disturbance and evaluate the system response. On time domain simulation, you design, you already simulate the system in open loop. You simulate the system in open loop. Here, what you will do is simply you will add these two equations, x5 dot and UBSS dot. So you have now 6 differential equation needs to be solved by Euler method or trapezoidal or Runge-Kappa or ODE function in MATLAB. So the only addition here is these two states of the power system stabilizer. You have all the parameters now are known in case T1, T2, and TW. So you can add these two equations and you can simulate the system with the power system stabilizer now installed. And you can, of course, do some disturbance in terms of mechanical power and reference voltage, and you can see the performance of the system. Maybe this is for the open loop, and definitely we need this for the closed loop system. Damping would be better. Any question, Shabab? Any question? Ramadan.
Yes, computing zeta. If we have multiple complex number for eigenvalues, which zeta we have to select and compare if we're meeting the design specification?
Okay, here for example, let us say you have A matrix. We will see just now an example. But anyway, let us, for example, say you have AC matrix, right? The AC matrix is dimension is what? 6 by 6. Am I right?
Yes.
So you have 6 eigenvalues here. So assume the eigenvalues are as such. These are the 6 eigenvalues that you have. If you have stabilizer here, and this is the closed loop, and then you get the eigenvalues. We have 6 eigenvalues here. Now, what are the oscillation? What is the oscillation frequency that is within the range of 0.2 to 3 hertz? Which one? You have here 6 eigenvalues. What is zeta for this?
0.
Huh?
0.
ايه بس سيجما عندنا سيجما فقط. So zeta equal to minus sigma over square root of sigma square plus omega square. We have omega equal to 0. So we have sigma square here, sigma. So minus
1.
So it becomes 1. So right? So it becomes 1. Am I right?
Yes.
Or this one, if it is real, definitely zeta equal to 1. If we have only real, so zeta equal to 1. Here, how much is zeta? Zeta for this oscillating mode equal to plus 10 over square root of 10 square plus square. So this is approximately 1 also. It is well dampened لأنه you can see sigma equal to minus 10. معناها إنه البول is very far in the left hand side. Definitely this is minus 10 plus minus G1, so it is here. But this sigma, which is minus 10, this is a well dampened oscillation. So this is approximately 1. For this one, you have here zeta equal to minus 1.5 square root of 1.5 square plus 6 square. So you can have this equal to somehow this is 230 6 point something. So this one could be 0.25. Usually this frequency within the range of 0.2 hertz to 3 hertz. If you divide by 2 pi, definitely. We divide this is the omega, so we divide by 2 pi. So the frequency here is approximately 1 hertz. It is in this range. So this is the eigenvalues that we need to test against zeta. And this represents the electromechanical mode of the machine. Okay, this represents the low frequency oscillation within the range of 0.2 to 3 hertz. فانت you select, you can طبعا of course رمضان يعني to be precise here, and we have some mathematical methods in order to identify which eigenvalue related to which states. يعني في طرق, we have some methods. One of them is called residue, one of them is called the participation factors. This method actually, you have eigenvalues lambda 1 up to lambda 6, and you have also the states, which is from 1 to 6. You have 6 states, which is delta, omega, E to D, and so UBSS here at the end. So you have here 6 states and 6 eigenvalues. These participation factors will relate lambda 1 and lambda 2, for example, will be related to delta and omega. And you can have lambda 3 and lambda 4 related to delta EQ prime and delta FD. 5 and 6 related to X5, and طبعا here it is not one-to-one. You have to do some analysis through the eigenvectors, the right eigenvectors and left eigenvectors, and you multiply this and that, and at the end you get the participation factor. Assume that in the lambda 1 and lambda 2 has high participation factor with respect to the delta and delta omega. So this mode اللي هو lambda 1 and lambda 2 لأنه lambda 1 is positive and lambda 2 is negative. So this is one mode. So this mode is related to the electromechanical part of the machine, delta and delta omega. So this is of our interest. احنا مهتمين بالمود ده. This is our main focus. اللي هو this mode which is related to the swing equation, delta and delta omega. So you can do this through these methods, or طبعا of course with the single machine infinite bus we can by inspection. By inspection you can highlight which mode is related to the swing equation. As we mentioned, this is the guidelines here, and the frequency is between 0.2 to 3 hertz. And you can see there is no frequency here, there is no frequency here. But these eigenvalues are out of the picture, and we have here the frequency is very low, or you can have this is equal to 30 مثلا. 30 if you divide by 6 يعني 5 hertz يعني out of this range, you can neglect this. And usually برضو يعني you can also say that the electromechanical mode will be the lightly damped mode. يعني if you are given مثلا minus 1 point plus minus, minus 10 plus minus, minus 20 plus minus. So which one will be related to the electromechanical mode? You will pinpoint this one directly, which is the lightly damped, minus 1. Minus 10 is well damped, minus 20 is well damped. So this is also another, by inspection you can easily pinpoint which mode is of our interest. So you can calculate zeta as such. Did I answer your question?
Yes, thank you.
Okay, comparing the eigenvalues between A and AC, and also you can do some time domain simulation, design a process for 60 Hz, single dimension from bus and so on. So compare the eigenvalues with and without person data system. So this is the data of the system is given here. You have the generator inertial field time constant and D equal to 0, xd prime, xq, KATA, line values, line impedance, load. You have local load here at the machine initial state. This is the operating point in order to get the initial condition and linearization constant. And okay, so this R is negative. Maybe you can ask why this R is negative. This is a transmission line. How the R is negative? Actually, in some of the in that commercial software, which is called PSSE, used in Saudi Electricity Company or utilities in general. This is worldwide very famous in transmission planning and so on. This PSSE, you can do some kind of reduction, or you can net some generation with load. This R is not a physical resistance, but it is it is an equivalent resistance to some of the generation which is netted with the load, which is combined with the load. So this comes from a generation here, this R. So negative R stems from deriving the one machine infinite bus model from a multi-machine system by equivalencing smaller generators by equivalent impedances with negative resistances. And actually, in real life, when you have, as we mentioned before, we have different levels of voltages. And you have some power plants are connected directly through a step-up transformers to 380 kilovolt. The big power plants are connected directly to 380 kilovolt transmission lines. Some of them are connected to 380 kilovolt, to 230 kilovolt. Some of them are connected to 115 kilovolt or 132 in central region. Some of them are connected to 69 kilovolt. Maybe in the MEM area you can have some plants which are connected to 69 kilovolt. Usually when you want to carry out a stability study, it is very difficult to consider all the plants. And all the plants will be very huge values. You can say, I will limit myself to 230 kilovolt and the 380 kilovolt plants. So I can reduce from being hundreds of the power plants to few power plants like 30, 40, 60. If you limit yourself to 380 kilovolt only, so you have fewer power plants and so on. So if you limit yourself to 230 kilovolt, okay, I will consider only in my study the plants that is connected to 230 or 380 kilovolt only. What about the plants which are connected to 115 and 69? You are considering them as a negative load, these power plants, or you net them with the load. and you equivalent them with the load, and you have like a load, equivalent load for the generation and load. And in this case, you may have this negative resistance here for the transmission lines. Okay. And of course, how to proceed for this? This is very simple. You have all the information that can you have the initial condition you can get, linearization constant you can get. You can build A matrix, AC matrix, and you can design the bar system stabilizer S equal to J omega 1, omega n. You can have omega n is K1 and so on, as we mentioned earlier. And you have, you can get the angle of GE, the angle of GC, and you can design T1 selecting T2 equal to this. The TW you can set it equal directly, and zeta n equal to, so you can get a KC. You can easily design the bar system stabilizer, and you can check the closed loop eigenvalues and so on. And this is straightforward. These are the initial conditions. These are the linearization constants. And the bar system stabilizer, you choose the following values. You choose zeta n, you choose T2, you choose TW, and you get T1 and the KC. So the results are omega n equal to this, angle of GE equal to this. The magnitude of GE, we need it, of course, in calculating the gain. So T1, you can get a T1 with this angle. You can calculate T1. We already discussed how to calculate T1. The KC with the magnitude of GE, magnitude of GC, and the K2, and the expression is there. You can get the KC. Therefore, the bar system stabilizer reset block. So this is the function, the transfer function now, the bar system stabilizer. The gain, washout time constant, you set it, and this is T1 and this is T2. And then you can form the A and the AC matrix, and you get the eigenvalues, open loop eigenvalues, and the closed loop eigenvalues. So definitely this is the electromechanical mode. You can see it is negative. It is on the right hand side, the system is unstable. And now this is the bar system stabilizer. After designing the bar system stabilizer, this eigenvalue becomes -1, so the system becomes stable. And you have here 6 eigenvalues in this case. In order to verify or validate this, you can calculate. And of course, if you look at this, which one is poorly dampened oscillation? Which one of those is poorly dampened? These are out of the picture, and there is no oscillation here. So which one is poorly dampened? Of course, the first one. So you can get the zeta here. You can calculate zeta here. Zeta equal to minus this square root of this plus this square. So this is the open loop. You can see the eigenvalue is negative. System is unstable for open loop. For closed loop, after designing the bar system stabilizer, the or the damping coefficient becomes 0.25. Of course, you set it at the beginning equal to 0.3, but after designing the bar system stabilizer, you have it 0.25, which is acceptable. And there is no big issue here. Of course, we expect some drift. We call it eigenvalue drift, and we assume a certain damping coefficient, but after design, and we have, of course, interaction between these modes together. It is not only we don't have only that mode in the system. We have other modes that contribute also to the oscillations, and in this case, you can have this close to whatever you set earlier. But this is acceptable design, which is close to the design, which is what is designed for. So this is the how to design the power system stabilizer. If you have any question, please ask. Saad Ahmed?
Yes, doctor. I was I was designing using these calculations. I was designing the power system stabilizer coefficients, but the problem is if you increase the instability too much by increasing the X line of the system, K1 can become negative. So then the PSS does not work. So how do we resolve this issue if K1 becomes negative?
if you increase the reactance, in this case you are pushing, increasing the reactance means what? Increasing the reactance means if this is your B delta curve, if you increase the reactance, then you have this is B delta curve, right? So if
Yes.
this is the even if this is the B mechanical, so system is there is no feasible point. Even if this is B mechanical, let us say. So instead of having this and this is the maximum, you are far from the maximum. Here you are very close to the maximum. System stability margin is very, very low. The stability margin, right? And you are decreasing the stability margin. But definitely, if this is the case, you need to. But of course, I don't know in this case. Do you have some operational solution, or you need to go for planning solution? For planning solution, you need to add an additional line. You need to add series capacitor or FACS devices in order to improve the system stability. This is in planning, as a planning solution for this. And for the operational, you need to reduce the operating condition or operating power or the initial condition.
All right, doctor. Thank you.
Okay. Any other question? Any other question? Okay, and I assume things are clear as far as there is no question in terms of the design, the steps of the design power system stabilizer and the block or the blocks of the power system stabilizer, function of the reset block, function of the lead lag, and so on. So, and I assume everything now is clear. So let us move to the last part. Last part is very straightforward, and this is just general discussion where we are here. We will discuss here the methods for improving the system stability. What do you think? Can discuss it just roughly كده before going down to these issues. What do you think if we need to improve the power system stabilizer? What are the actions that should be taken? Any clue? Any suggestion? How to improve the system stability? Ramadan.
Said that we can install FACS devices or new transmission lines.
FACS. Fax devices. Yes, you are right. This is one way to improve. You have series compensation, you have shunt compensation, SVC or STATCOM, the shunt compensation, you have triple SC and thyristor controlled series capacitor or series or switched series capacitor also. So you can have the fax devices will improve the stability. We did it already, we discussed it before how the stability margin increases with the fax device. What else? Second, Hussein.
Speed up the fault clearance.
Yes, of course. If you have a faster circuit breaker, if you can detect the fault very quickly, this will improve definitely the stability, and again, you will not reach to the critical clearing time. You are far from the stability verge or stability limit. So you can have a faster circuit breaker, faster relays to detect the fault. And nowadays, recently, SEL company produces a circuit breaker, a relay, which depends on the traveling wave that can detect the fault in 4 milliseconds. 4 milliseconds means 1/4 of the cycle. And in 1/4 of the cycle, you can detect the fault, which is very short time, by the way. Very short time by traveling wave-based relays. So you can detect the fault very quickly. And if you have very fast also circuit breaker in one cycle, they have now in one cycle circuit breaker, so you can detect and isolate the fault very quickly, so you can improve the stability of the system. Okay, Hussein, what else? Any other suggestion?
Using the power system stabilizers.
Of course انا هزعل قوي لو انتوا ما فيش حد قال لي الباور سيستم ستابلايزر ده احنا عاملين now we are discussing this design of the power system stabilizer to improve the stability and so on. So definitely through the excitation system, we can design power system stabilizer to improve the stability. What else? If we have fault, and this swing equation we have fault and this becomes 0 مثلا. So the machine will accelerate. Am I right? The machine will accelerate.
Yes.
And the frequency will go up and up.
Yes.
طيب, how to limit this frequency increase? Saad Ahmed?
I don't know about limit, but I think we can slow it down with spinning reserves or things like that.
You can have, we can have what we call braking resistor. You have your switch. This is called the braking resistor. If the frequency goes high, if this power is approximately 0 or very low, and you have here a positive difference between in this case, you need to inject a load here, which is the resistance. طبعا this is of course resistance. مثلا size of this resistance is 100 megawatt. It is not يعني just small resistance. لا, you can have 140 megawatt even in real life. A resistance that can dissipate 140 megawatt. So this is a resistance here that can be inserted to the system to increase the electrical power. So we can reduce this. So one of the ways to improve the stability is a braking resistor if we have fault. But what about the opposite? What about the opposite? If we have like negative accelerating power and the frequency is going down and down, so how to limit such frequency decrease? Omar.
Yani, if we have some reserve, like spinning reserve, we can quickly try to inject that into the grid to support the system, or we can quickly shut down some loads.
Yes, under frequency load shedding.
Yes. Yeah, but Doctor, I want to ask, the one you called braking reserve, is it the same thing as a dump load?
Which one?
Number 4, braking resistor. Is it the same as dump load?
Yes, you dump the load to the system.
Okay.
You dump the load here, but this is not normally. It is not connected.
Yeah.
And in steady state, this is of course not connected, but we can connect it if we have a fault. And actually, due to this very huge megawatt of this, so a lot of heat, dissipated heat here, you switch it on and off in a certain scenario. You can put it in few milliseconds and put it off, on off, and so on. So you have some switching scenario here.
Usually automated, Doctor?
Sorry?
Usually automated, right?
Of course, طبعا it's not manual. And this is thyristors, and these switches could be thyristors. And of course, you have a control. Depends on, مثلا, for example, the frequency. If the frequency goes to 61, then you switch it on. If it is below, then you switch it off. And it's go on, off, and so on. And this is, of course, you have a control, scenario here. So under frequency load shedding also could be one of the solutions if we experience a decrease in the frequency. Hussein, you have another method to improve?
Yes, the interconnection systems, also the energy storage system.
Yeah, of course, all these issues could help. But this is, of course, you need some of the planning phase, the interconnection and also energy storage systems. This will improve طبعا the reserve and will improve the frequency regulation. What else? طيب, okay. Of course, we can add some of the issues here. Similar to facts, we can have shunt reactors or series capacitors. We can also, let me ask you, if we have circuit breakers, usually circuit breakers will trip the three phases together. Am I right? And if we have a single line to ground fault, if we detect the fault, then the circuit breaker will isolate the three phases.
Yes.
If we have the circuit breaker isolate only the faulted phase, if this will this help in improving the stability or not? If we isolate only the faulted phase, not the three phase together. Omar.
It will not.
Yeah, Omar.
Because the system will be imbalanced, so it will not.
لا الامبالانس yes you are right. الامبالانس has some of the issues. يعني but هل الامبالانس معناه ان السيستم is unstable؟
Yes, at the moment where that single phase was isolated, yes, it will improve this. It will stabilize the system. It's going to improve. It's going to show little improvement. But I think after some time, the system will become destabilized again.
يعني if you still have two phases intact.
Yes.
Two phases are intact and you are still sending the power through these phases. Will this help in improving the stability or not?
It will.
It will. Yes, you are right. It will help. It will help in improving the stability. You are not, isolating all the phases and we remove the line. We don't remove the line. We remove only the phase, the faulted phase only. So we keep the line. يعني مثلا, for example, if you have here two lines as such. If you remove this line, that means your system, your power will be halved. And almost will be halved here. Right? If you remove this line. And then
Yes.
if you remove only one phase of this line, so you're still sending power here. So the power angle will improve here. And in this case, you extend the stability limit. So you can have what we call single pole circuit breaker. Single pole switching. Abdulaziz Khalid?
Dr. but from a point of view, for example, in most industrial facilities, most of our loads are like three-phase induction motors. So I don't think it's possible in this case to only isolate one phase. This is what I understand, but correct me if I'm wrong, right?
You are right, لأنه زي as we mentioned إنه يعني currently the circuit breaker will trip all the three phases. If you trip only one phase, in this case you have unbalance, and this will affect definitely the induction motor performance. You have a lot of harmonics and vibrations and so on. There are some challenges for the single pole switching, but if we focus on the stability, improving the stability, yes, it will harm the system in terms of harmonics, vibrations, heating, and so on. But this is for very short time where we need to keep the system stable. We need to preserve the system stability. And usually when you have a circuit breaker, you trip or you isolate the faulted phase or faulted line, and then the circuit breaker will close again after 3 cycles or something like this. And if the fault is cleared by itself, then most of the faults are cleared by itself. If the fault is cleared, خلاص, that's fine, we will go smoothly. If the fault is not clear, the circuit breaker will open again and you may repeat this once again and so on. So if you remove the faulted phase for 1 cycle or 2 cycles or 3 cycles, and then you close the circuit breaker back after 3 cycles, يعني 0.5 50 millisecond, 3 cycles. After 50 millisecond, you close again the faulted phase. And fortunately, the fault is cleared by itself. And you be back for the 3-phase system normal operation. So this would help the system stability, Abdulaziz, or not?
Yeah, if it is for a very short period, I think.
Yeah, of course, we cannot work on unbalanced system for a long time. This, as I mentioned, you will have harmonics and you will have unbalance, and then you have vibrations and the induction motors and so on. طيب عمر, what is your question, Omar?
Yes, Doctor, I want to make a comment that in the industry, most heavy machines that are powered on 3-phase systems usually have some kind of control device installed with them that when 3-phase faults, when they say phase faults occur, maybe one of the phases is gone, or maybe there's a phase change. So they have some kind of devices that will compensate for the phase change or for the phase loss within some time, within certain frame of the time that the system misbehaves.
Okay. Okay, so and you mentioned that we have some devices to compensate the faulty phase, or what? Did I get your point as such?
Yes, like there is a device called phase correction, for example. It's the heavy machines in the industry, usually in the manufacturing industries, they are built like as if they are panels too. So usually the power is supplied through that device before it is used to power the machine, for example. So in a case where there's faults, there's some kind of unbalance on the network that is supplying that 3-phase device. So the phase correction device would quickly, either if there's a phase loss or there's a phase change, such that it can affect the operation of the machine. So that particular device will quickly help to compensate at that few seconds.
Yeah.
It will not be able to last for a long time, but it's.
If this is the case, yes, it will improve the system stability then. طيب Hussein?
Yes, Doctor. I just want to add a comment also related to this issue of single pole tripping. Actually, it depends on the system configuration. If the planning, they already considered this situation at the beginning of the design of the network, it could be possible to have it. Here in Saudi Arabia, we have single pole circuit breaker at the EHV side for 230 kV and 380 kV. And it could be done with certain modification to have single pole tripping for, as you just mentioned, since most of the single phase faults is just temporary, and when they just break the single pole and they auto close it again, the fault will be cleared. So it can be done.
Yes, you are right, especially for, as you mentioned, for the interconnection lines, for tie lines, which is very critical to the central operating area, to western operating area, or central operating area. This is the very crucial tie line to isolate it completely, the 3-phase. So if you can have only 1 phase off, and then after 3 cycles you reclose it again and you regain your system, so this will be okay. طيب, okay, يعني this is just a reading material that you can go over it quickly. We discussed all of them. Here, machine excitation, power system stabilizer, machine mechanical loop. If you also have what we call the fast valving. And we assume and the B mechanical is constant. But if you have a B mechanical that can be reduced, if you have a fault, we need Bm minus Be. Be becomes a 0. So to increase it, as we mentioned, we have braking resistor and so on. But one way also is to reduce B mechanical, is to have fast valving. In very short time, you can divert the steam going to the turbine, so you can reduce the turbine. Of course, this will affect mechanically the turbine, يعني الروتور mechanical fatigue of the rotor and so on, لأنه due to this fast change of the power network, as we mentioned, the fax devices and so on, shunt compensation, series compensation, protection, clearing the fault as fast as possible, and also for single pole switching and so on. So these are the reading material actually. It is just very simple. These are the main major objectives. I know and I exceed the time, but and if you give me just 2-3 minutes to go over it quickly, or you can if you have any difficulty, we can discuss it next class, inshallah. Okay. High-speed fault clearing, reduction of transmission layer reactance. You can have series capacitor and so on. This is just, you can go over this, and then if you have any problem, we can discuss it. Fast valving, generator trimming also will improve the system stability. Very short time separation, load shedding, high speed excitation, and the power system stabilizer. Okay, so please go over it, and we can discuss it more next class, inshallah, for this. Any question? Any question? If there is no question, so we can end our class. Okay.